Fun with pi. You learn about pi early on in your math career, circumference, area, some digits, stuff like that, and here it is again. But what's going on here? I'm pretty much just repeating stuff from other videos here, but I wanted to do this whole thing in some detail, because it ties together all sorts of topics in calculus, and I also wanted to include a tool for estimating the value of pi, so let's do it. Factorial suggests a series, sometimes, but what the heck is 0.5 factorial? It is our invitation to use the gamma function. I said we'd be doing calculus, so here is our big nasty integral. But where does the pi come from? Here, lemma 1, Gauss's integral. You know it from the bell curve. There's the shape with the mean and the standard deviation. There's the function in terms of x, a little bit simplified. It needs that as a normalization constant because Gauss's integral is equal to the square root of pi. And we're going to prove it. Call this I. Call that I. Multiply them together. I squared. This is over an area, all the area. Change to polar coordinates. R goes from 0 to infinity, and theta makes one complete circle. Still all the area. Rectangular. Polar. Equations. Area is length times width, or r dr d theta. That's how we change coordinate systems. Take out the 2 pi, borrow a -2, integrate over the correct limits, find I squared, which tells you the value of I. Lemma 1 complete, pi acquired. But we've got much more work to do with t, a dummy variable, and dt, and a cute substitution trick. This is the cute part here. And the integral now looks like this, which is just begging for integration by parts, which is something I can never remember how to do. But I do remember the product rule, rearranged, integrated. Technically, I think this is integration by negative parts. More dummy variables. And another problem. That first term there, that's a problem. That's infinity over infinity. So what do we do here? We call for help. L'Hopital's rule, with two functions, f and g. F and g. What's the limit as these two functions go to infinity? Well, clearly the red curve gets there faster, it's steeper. Slope to the rescue. What's the limit as these two functions go to 0? 0 over 0? No. Slope to the rescue again. F of x gets bigger faster and smaller faster. L'Hopital's rule applied here. And it's not even close. E to the t squared by knockout. And that leaves us with Gauss's integral. Almost. See, the limits are wrong. From 0 to infinity, well, we wanted negative infinity to positive infinity. Luckily for us, the bell curve is an even function, like cosine, symmetric about the y-axis. And that means that doubling the integral doubles the integral. But we're moving in the opposite direction, and we're done. Halfway done. Our next challenge is to prove that pi can be expressed as a series. Let's graph it. The value jumps back and forth, too high, too low, too high, too low, and this line gives the average of the preceding two values. After about 13 terms, we're settled in at about 3.14, which is about all I probably trust myself to measure anyway. It's a power series, and these serieses only converge when a is between -1 and 1. Otherwise, they go crazy. Here's a power series that might make sense to you. It converges, as you can see here, because the terms get smaller and smaller and smaller. Okay, get your power series and multiply it by a. Again, a is less than 1, so this makes it smaller. Then subtract the 2 and factor out a q and divide, an expression for your infinite sum. And if you're wondering why plugging in a equals 1/2 would give us not the value 1 we saw before, but the value 2, well, that's because when we did it before, we left out the 1/2 to the 0 term equals 1. Our first term was 1/2 instead of 1. Anyway, that's the problem. Here's q and another dummy variable. Hey, that gives us our add, subtract pattern. Nice. And this might look familiar if you know your special integrals, and if not, we have another lemma. Using some facts about trig functions, which we'll take as a given, I hope you know them. If x equals tan y, that's sine divided by cosine, which is a chance to use the quotient rule, which is another rule I can never remember. So I just go back to the product rule, which is a little bit tricky this time. I'm putting the derivatives in the brackets, but it simplifies to this, which is oh so clever. Another cute trick here, especially when you take the inverse of both sides. Did you know you could do that? And this is something to hold on to as we go back to Q and integrate from 0 to 1. Y, you'll see later. All those terms on the right, not too bad. If you've brought along your power rule, you can integrate those. But what about this 1 over 1 plus b squared nonsense? Well, that's what the arctan was all about. Evaluate it from 0 to 1. What angles would give us these values? To the unit circle. Looking around here, found it, and I found the other one too. But wait a minute, I got a tough question. What about those values, huh? Why can't I use those values? Can you think of an answer? I'll give you 3 seconds. That's why. I told you that would be important. Did I say that? I meant to include that. Anyway. Remember this sequence? Remember 1/2 factorial? Well, that means if you were to plug in this monstrosity into your calculator and keep going and going and going, it would get down to 0 eventually. I guess I'd have to try that if I put that in there, so I'll give it a few terms here. Maybe I can do this at a faster speed. Fun with pi. You learn about pi early on in your math career, circumference, area, some digits, stuff like that, and here it is again. But what's going on here? I'm pretty much just repeating stuff from other videos here, but I wanted to do this whole thing in some detail, because it ties together all sorts of topics in calculus, and I also wanted to include a tool for estimating the value of pi. So